In this lesson, we'll be covering AC series circuits. And as a review, we'll recall that AC voltages and currents are represented by phasors, and that the current through and voltage across elements are related by their impedance, which is a complex number. So this is just a generalization of Ohm's law, where initially we had V equals IR for DC circuits, but now we're going to convert that to V is equal to IZ, where all of these are now vector quantities. And Z is complex impedance instead of just resistance. So depending on how the problem is presented to us, we may be given a time domain problem where we have sine waves, where we need to convert to the phasor domain and then get our answer back into the time domain. However, there are other times when we will just be given the phasor quantities from the get-go, and we will just solve our problem completely within the phasor domain. So depending on what is required of us, we just need to be cognizant of the fact that when we're going back and forth from the phasor domain to the time domain, we just take our voltage RMS value from our phasor and we place that in the amplitude of our time domain, but we have to scale it by a factor of √2. Likewise, we will take our phase angle in the phasor domain and place it back into the time domain sinusoidal function. For AC series circuits, though, combining impedances is very similar to how we combine resistances in DC circuits. Series impedance is just the summation of the individual elements in series, where this time though, however, our impedances are complex quantities, and so it now becomes a vector sum as opposed to a simple arithmetic sum. So here we see, our Z total is equal to Z1, Z2 plus however many impedance elements we have in a given circuit. So here is a demonstration. Our Z total in this case would be this resistive impedance, R of 3 ohms, and this inductive reactance of 4 ohms, right here. However, when we add them together, though, we need to be cognizant of the fact that we are just given the resistance and reactance in this case, and we need to make sure that we are translating them into impedance, And what that really means is just adding the proper J, whether positive or negative, corresponding to inductive or capacitive impedances. So here we go. In this case, Z of t is equal to positive 3 ohms plus J 4 ohms. And that is our quantity in rectangular terms. We can also convert it into polar form if we wanted to, and we would get 5 ohms, angle 53.13 degrees. So here in the second example, now we have a resistive element, inductive element, and a capacitive element, all in series. So again, we just need to make sure that we capture the imaginary J added to our inductor and the minus J added to our capacitor. We find the sum of all those quantities and we get both our rectangular and our polar form of our total impedance. With the introduction of this positive and negative J terms that we can have for an inductor or capacitor, we have this special case where the reactances could actually cancel out if they had the same magnitude. And if they were the only elements within a circuit, we would actually get a short for that part of the circuit. Once we've found the Z total for a given circuit, we can determine or classify the circuit as either resistive, inductive, or capacitive based on the phase angle of this impedance. So if the angle is 0, we have a resistive circuit, right? And that will correspond to when our reactance is equal to 0. If the phase angle is greater than 0, the circuit is inductive. And if the phase angle is less than 0, our circuit is capacitive. And we can prove that by using, again, Ohm's law that will give us a phase angle greater than or less than our voltage, depending on what the phase angle of the impedance is. Now we'll also take a look at Kirchhoff's voltage law and the voltage divider rule. Again, the same principles apply, however now we're dealing with phasors for our voltages, and our resistors are now being replaced by impedances, which are complex numbers. So here we have Kirchhoff's voltage law, and the phasor sum of voltage drops and rises around a closed loop is equal to 0. So for this circuit right here, right, we have a voltage rise in the form of this source, and then we have 3 voltage drops with this resistor, inductor, and capacitor. All right, and if we solve for this voltage drop across the capacitor, we'll set up an equation like this, where we just sum all of the vector quantities for the voltage drops that were given in the circuit. Right, and although it's in polar form, we can easily change that into rectangular form if we needed, which is a bit easier to use for addition or subtraction. However, we should generally be using our calculator for this, so in that sense it really doesn't matter whether it's in polar or rectangular form. Also, the voltage divider rule, again, only changes now are we have the phasors for voltages and currents, and we're using impedances now instead of resistance. Alright, so we'll take a look at this voltage divider formula, and I'm going to perform a small tweak so that it is written how it is on your equation sheet, right? And we have Z of x, which is the impedance of interest that we're looking for the voltage drop, over, right, Z equivalent, which is the equivalent impedance for the series elements, and we'll multiply that by the voltage drop across that equivalent impedance. Okay. So we see here, if we wanted to see the voltage drop across this capacitor, we would put the impedance of the capacitor in the numerator, and then the sum of all of the impedances in series in the denominator, multiplying that by the combined voltage drop of all of those impedances, which we know to be 10, again based off Kirchhoff's voltage law. Right, so if we plugged in, right, the minus 3J, the impedance of our capacitor, and then we have that over 4 plus 6J minus 3J. Right, and although these are all in kilo ohms, right, what we're doing is that we're just pulling out that kilo ohm term and canceling it out, since it's common to all of the impedance elements in this circuit. Right. So we can actually plot the impedances on a single plot, showing the individual impedances, and by using the vector sum we can come up with the total impedance for a given circuit, and this is referred to as an impedance diagram. It is not technically a phasor diagram because an impedance does not correspond to any time varying term. It is a constant value for a given frequency, so it is part of an impedance diagram and not a phasor diagram. So for here, in example 1, we have a very simple series of elements, and we're asked to find the total impedance for it. So for this step, I'm going to rewrite it as C of R, which is equal to 4 ohms, and C of L, which is equal to J 8 ohms. And Z total just becomes the vector sum of these quantities. And if I wanted to, I could rewrite this in polar form, and you would come to 8.94 ohms, angle 63.43. Alright, this example also asks us to plot this out on an impedance diagram. So we'll have our real and imaginary axes. We have 2, 3, 4 for our resistive, and 1, 2, 3, 4, 5, 6, 7, 8 for our imaginary. So our impedance would be that, right, giving us a magnitude of 8.94, and our angle 63.43 degrees. Right, and as you may notice, that is not to scale. And I will just make sure to label this as C of T. This quantity C of R, and this one as C of L. So we'll move down to another example problem. We'll go to example number 3. Right, so we have a network total impedance, Z total is equal to 24 kilo ohms, angle minus 30 degrees, frequency of 2 kilohertz. Alright, and the question asks, with 2 series elements, what type of components are these, and what are their resistive, inductive, or capacitive values? So, from this, we can find that Z of T, and we'll write it in its polar form. But then, plugging it into our calculator, we will convert it into rectangular. So we get 20.78 minus J 12 kilo ohms. Now that we have this total impedance in rectangular coordinates, we can deduce a lot of information from it. And right off the bat, by seeing this real term, we know that there is a resistive element within those 2 impedances. Right? If it was only inductors or capacitors or some combination of inductor and capacitor, it would only give us an imaginary component in this impedance. Right? So with this real component, we know that one of the elements is a resistor. And then if we take a look at this minus J, right, that points to having some sort of capacitive reactance, right? That is a negative reactance that we have, so we have a capacitor. So our 2 components are a resistor and a capacitor. Now to find the respective values of the capacitor and resistor, well, we know that our resistor, right, is independent of frequency. So our resistor is 20.78 kilo ohms. Okay, pretty straightforward. Now our capacitor, on the other hand, we have minus 12, and using our formula to calculate the reactance from a given impedance, so we have 1 over 2 pi frequency times our capacitance. We will rearrange the terms on this, so we have solved for C, which is equal to 1 over 2 pi F times the reactance. We'll then plug in the terms, so 1 over 2 pi, our frequency is 2 kilohertz, and we have 12 kiloohms. Plug that into the calculator, and we will get 6.63 times 10 to the negative 3 farads, which is equal to 6.63 millifarads. So we'll go ahead and do one more example. Scroll down right here. Alright, in this problem we have a set of series impedances connect to a voltage source, and it asks us to use voltage divider rule to find the voltage of this inductor right here. Okay. And then once we've done so, to determine the value of that inductance. Okay. Alright, so we analyze the circuit. We see that they give us the time domain representation for our voltage source, so we need to convert that into a phasor. Right, so we take our peak value, 294, and divide that by root 2, and then add the phase angle, which we get right here. Alright, and that gives us 208 volts with a 0-degree phase angle. Alright, so next step is to create our equivalent series impedance, right, which is just the vector sum of all the series impedances. So we have 600 for our resistor, and then we have a positive J 200 for our inductor, and a minus J 300 for our capacitor. Alright, so combining our two J terms, we get a total of 600 minus J 100 ohms. Okay. So next we'll use the voltage divider rule. So V of L is equal to, right, in this case, our source voltage times the impedance of that inductor over, right, that total impedance. So if we plug in the values, we have 208 volts. Multiply that by the inductor's impedance over the total impedance. And again, the trick here will be just to enter it in the calculator correctly, making sure you use the parentheses appropriately. And our final answer comes to 68.4, angle 99.46 degrees, volts. Alright, okay, so that answers part A, and leaves us part B, which asks us to determine the value of the inductance. Well, if we know that our reactance value is equal to omega L, which is equal to, in this circuit, 200 ohms, we can rearrange our formula so that we can solve for just the inductance, which is equal to that reactance divided by omega. Well, omega is offered to us right up here in that time domain representation as 377. So this simply becomes 200 ohms divided by 377. Right. And that gives us 531 millihenries for our inductance. All right. That concludes this lesson. If you have any additional questions, please refer them to your instructor.